Hello science fans, physics paper 2, this is Waves video 4. It uses the same piece of paper as Waves video 3, but hopefully you've watched video number 3, which is all about electromagnetic waves. When we looked at that, you might remember that I reminded you that electromagnetic waves have got 4 properties, and we looked at 3 of them, but we didn't look at refraction. And that's because we're going to look at refraction in this video, so we need to know about that in more detail. But before we look at refraction, I need to remind you about something called ray diagrams. So just get the right bit of paper under the camera here. Okay. So ray diagrams are a way which we can show how a wave is going to behave, or a ray of electromagnetic radiation is going to behave. They look slightly complicated, but they're actually quite simple, so they're not too bad. First of all, we start with whatever surface that the ray of light is going to hit. In physics, we call that being incident upon. So the ray of light is incident upon the mirror. We mean it hits the mirror. Okay, and you can see that we have a ray of light coming in and it hits the mirror and it bounces back out. So we kind of know about that, that's reflection. But let's just get into the detail of the diagram. So the first thing we do is we draw our surface. In this case it's a mirror, and we label the surface. The next thing we always do is we draw a dotted line at 90 degrees to the surface. And I put the little symbol we use in maths there to show it's 90 degrees. And this line is called the normal or normal line. And in physics, the word normal means at 90 degrees to. So we have our mirror or our surface, and then we have the normal line, which we always show as dotted, and we have that at 90 degrees to our surface. The next thing is we show the ray of light or wave that's going to be hitting the mirror or the surface, and we show that as a line, and it's really important we put an arrow on it part way down. We don't put it at the end, we put it in the middle somewhere. But if you don't put that, you lose marks on the exam, so make sure you do that. Then we can measure an angle to do with this ray of light, and we call it the incident ray, by the way. If you remember, incident means it's shining on the mirror, so we call the ray that's coming in the incident ray. And any angles to do with ray diagrams are always measured between the ray and the normal. We don't bother with the angles down here at all, we're not interested in those. So we can measure the angle between the normal and the inbound or incident ray of light. We call that angle the angle of incidence. Then we can draw what happens to the ray, and in this case it's reflected, so it bounces back out the other way. And again, we show that the ray of light with an arrow on it, really important, somewhere in the middle, to show which direction that ray is moving. This would be equally true for an X-ray or a radio wave or an infrared or microwave. These diagrams are used for all types of wave. Okay, and again we can measure the angle between the normal and the reflected ray, and we would call that the angle of reflection. And sometimes we use a little I and a little r to show that. So that is our ray diagram. Right then, there is a slightly sort of developed version of a ray diagram called a wave front diagram, which you also need to know about. And when I'm teaching this in class, I always say to students, imagine if you're looking out to sea and there are lots of waves coming in. They actually don't come in as a single point coming out from deep in the sea in towards the beach. They actually come in long lines, don't they? And if you were in a helicopter above them, you would see long lines. So perhaps you would see something like this, these long lines of waves heading in towards the beach if you were in a helicopter above that. And really this diagram just shows that, because if you look at my other terrible drawing here, it's meant to be a light bulb. We don't have one ray of light coming out of light bulbs. We actually have many millions of rays of light coming out of light bulbs. But if you start to try to draw that, it gets really confused really quickly because all the different rays just get mingled and mixed up with each other. So what we actually do to show the fact that waves actually travel, there's lots and lots of waves all travelling as what's called a wave front, and that there is a wave front, that line. So if we're hovering above the ocean in our helicopter, each of those lines showing a whole wave travelling forward is called a wave front. So that bit there is called a wave front. So we can draw that on a diagram. It's just like a ray diagram. There's our mirror at the bottom. There's our normal or 90 degree line shown as dotted, and there is a single ray of light travelling in, the incident ray with the arrow, and then it reflects back out with the arrow showing it's going that way, and then we just draw the wave fronts at 90 degrees like that. So it's a bit like being in that helicopter above the ocean. The only thing to note is where the waves hit the surface, we don't draw them underneath there, we show them stopping at the surface. So that is a wavefront diagram. It's not very different to a ray diagram, it just shows that there's lots and lots of rays all doing this at once, not just the one ray that we're showing. Okay, last thing on this video that we need to look at is refraction, which is a fairly big topic in itself. So the first thing to remind you, it's refraction, not reflection. Reflection is what happens in a mirror, but refraction is what happens when a wave passes from one medium to another. When we say medium, we mean the thing it's travelling through, like for example the air or water or glass or perhaps a vacuum out in space. When a wave passes from one medium to another, so let's say from air into a block of glass, it changes direction, and that change of direction is called refraction. The denser the medium that we're talking about, so glass is more dense than air. What I mean by that is that a cup full of air and a cup full of glass, well, the glass is going to weigh more because it's denser. The denser the medium, the higher the refractive index. All that means is how much it refracts or bends the light. So the denser the medium, the more it bends the light, but we call that having a higher refractive index. Okay, so we're going to look at this using a ray diagram. Okay, we're using this top ray diagram to start with, the one with a block, a glass block here. So I've drawn a glass block, and we've got our ray of light that is incident on the glass block. What that means is it's travelling in towards the glass block. Where it hits the glass block, I've drawn my normal line. I should have said on the ray diagrams, the normal line is always drawn at the point where the ray hits the surface. So the ray hits the surface there, I've drawn my normal line, and I've shown that there's a little 90 degrees there, so we know it's the normal line. But look, when the ray of light passes into the glass, it changes direction. It doesn't scoot off down there, and in fact it bends in towards the normal. The reason it bends in towards the normal is because glass is denser than air. So we've got a little rule which I've written here. So glass is denser than air, so the light bends towards the normal line. Okay, so now it changes direction for a little while until it gets to the other side. This is called a boundary between the two different mediums. Okay, it's just the edge of the surface really. So the ray gets to that point, and then once again it moves from glass into air. This time it's moving into a less dense medium because air is less dense than glass, so it bends away from the normal, and in fact actually it bends back so it's parallel with the original ray there. So that angle there, the angle of incidence, remember that's an incident ray, so that angle of the incidence will be the same as that angle it has when it leaves the glass block over there. This angle inside here, which is quite small, and so I had to kind of draw it on the outside, is called the angle of refraction. So that same normal line, when the ray changes direction, the new angle between the refracted ray and the dotted line, the normal line, is called the angle of refraction. Okay, that's different from reflection. We call the ray of light that's travelling through the glass, that's changed direction or bent, we call that the refracted ray. Okay, so ray of light hits a more dense medium which makes it refract or change direction, and it bends towards the normal because glass is more dense than air. When it leaves the glass block, it refracts or bends away from the normal because air is less dense than glass. Two more things you need to know about this. The first one is in the green cloud here. This only happens when the electromagnetic radiation, could be anything, it could be gamma rays, light rays, radio waves, you name it. It only happens when it's not hitting the material at 90 degrees. So if the ray hits the glass at 90 degrees, it doesn't change direction, it just passes straight through, as you can see. So there is no bend. Okay, so 90 degrees means no bend. 90, no bend. The only other one you're expected to know about is in the other green cloud here. Okay, and this time we haven't got a square glass prism. By the way, that's that word there. prism, it just means a block of glass, okay? So this time we haven't got a square prism, we've got a semicircular prism. And again, we've got our original ray of light, the incident ray, which is touching the surface of the glass at that point. I've drawn a normal line, of course, which is at 90 degrees, always is, just like that. And as we would expect from our previous diagram, the glass is denser than the air, so it refracts, bends towards the normal, so it changes direction, just like the one did in the square prism. But the change is, or the difference is, when it hits that curved surface, if you were able to zoom in on that area there with a microscope, you would see that actually it comes out at 90 degrees to that glass surface because it's curved. And that means it doesn't change direction again when it comes out, because it's hitting that surface at 90 degrees to the curve, and it just comes straight out. So there's no bend on the second part of a D-shaped or semicircular prism, okay? And that would be true if it hit there or anywhere else. So you only get one bend on the way in. Okay, that's it. Waves video 4. That's Waves finished. Well done.